The ground beneath your feet right now is moving, not metaphorically, not slowly over millions of years in some textbook diagram. Right now, centimeter by centimeter, day by day, the western edge of North America is being squeezed, pulled, and stressed from two directions at once. For decades, scientists treated these two forces as separate problems. Two giant geological systems, two independent threats, two different sets of emergency plans. But new research buried in the data from the ocean floor is telling a very different story. These two systems, the San Andreas Fault and the Cascadia Subduction Zone, are not separate. They are connected. And the moment one of them breaks, it may not break alone. What follows isn't a worst-case theory. It's a chain reaction that the geology of the West Coast has been quietly building toward for centuries. And understanding it may be the most important thing you do today. To understand why this matters, you need to know who the players are. The San Andreas Fault is the most famous crack in the Earth's surface. Nearly 1,300 kilometers long, it runs like a scar from the Gulf of California all the way to Northern California, slicing through cities, farmland, and suburbs. It is where the Pacific Plate and the North American Plate grind against each other. Not diving beneath, not separating, just grinding, locked in a slow-motion collision that stores energy the way a coiled spring stores tension. Southern California has lived with it for generations. Los Angeles sits directly on top of it. Scientists have watched it, modeled it, named sections of it. They know that the southern segment hasn't fully ruptured in over 300 years. That's not a comfort, that's a countdown. Now look north. Off the coast of the Pacific Northwest, from Northern California up through Oregon, Washington, and into Canada, sits something far less talked about but arguably far more dangerous: the Cascadia Subduction Zone. Here, the Juan de Fuca Plate is slowly diving beneath North America, not grinding sideways, but bending downward, like a slow-motion collision happening underwater. When this system fully ruptures, and it has before, roughly every 200 to 500 years, it doesn't just produce an earthquake, it produces a megathrust earthquake, a magnitude 9 or above. The kind that reshapes coastlines, the kind that sends tsunamis across the Pacific. The last time it fully broke was January 26, 1700. Over 300 years ago, the evidence is written in ghost forests, in sunken coastlines, in the oral histories of indigenous nations along the Pacific Northwest, and in Japanese tsunami records from the same night. Two faults, two threats. That's what the maps always showed. But the maps were incomplete. The discovery didn't begin with a dramatic moment. It began with sediment. Deep beneath the surface of the ocean, off the Pacific coast, researchers have been extracting core samples, long cylinders of layered sediment that function like an archive of the Earth's history. Every major earthquake leaves a signature in these layers: a turbidite, a sudden deposit of disturbed sediment that cascades down underwater slopes when the ground shakes violently enough. When researchers began cross-referencing the turbidite records from the Cascadia Subduction Zone with fault activity data from Northern California, they found something that shouldn't have been there. The timing aligned. Not perfectly, not every time, but in a pattern too consistent to ignore. Large rupture events on the southern end of the Cascadia system correlated with major seismic activity on the northern segments of the San Andreas Fault at a rate far beyond random chance. The question shifted from "are these systems linked?" to "how?" The answer lies at a place called the Mendocino Triple Junction, a geological crossroads located off the Northern California coast where three tectonic plates meet simultaneously: the Pacific Plate, the North American Plate, and the Juan de Fuca Plate. It is one of the most mechanically complex points on the surface of the planet. This junction isn't just a meeting point. It's a mechanical relay station. Stress doesn't simply stop at a plate boundary. It transfers. When strain builds in one system and the geometry is right, that energy can be transmitted into an adjacent system, nudging a locked fault closer to its own breaking point. Scientists now believe the Mendocino Triple Junction acts as a conduit between the two fault systems, a geological bridge that neither system acknowledges on a map but both respond to in the real world. Here's where the physics becomes as unsettling as the geology. Fault systems don't rupture randomly. They rupture when the accumulated stress along a locked section exceeds the friction holding it together. It's a threshold problem, like water held behind a dam. The dam doesn't fail a little at a time. It holds and holds and holds. And then it doesn't. What researchers are now modeling is a scenario where a major rupture along the southern Cascadia Subduction Zone, even a partial one, redistributed stress across the Mendocino Triple Junction and loaded the northern segment of the San Andreas Fault with enough additional pressure to push it past its own threshold. In other words, one earthquake triggers another, not hours later, not days later, potentially within minutes. The physics of this process is called Coulomb stress transfer. When one fault's movement shifts the stress field of the surrounding crust, and in doing so, either relieves pressure on nearby faults or increases it. In this case, the modeling suggests that a Cascadia event could increase the stress on the San Andreas, not relieve it. The sequence, if it plays out, would look something like this. A megathrust rupture begins offshore. The Juan de Fuca Plate lurches beneath North America. The seafloor rises. The coast drops. Waves radiate outward. But simultaneously, hundreds of kilometers to the south, the stress redistribution is already happening. The northern San Andreas absorbs the transferred load, and within a window that scientists measure not in days but in moments, that fault responds, back to back. Two major earthquakes striking the west coast in close succession, separated not by decades but potentially by a single night. The people who study these systems don't use the word inevitable lightly, but they're using it now. To understand what this kind of event looks like when it arrives in the real world, you don't need to imagine it. You just need to look at what happened in Japan on January 17th, 1995. The Great Hanshin earthquake struck at 5:46 in the morning, magnitude 6.9, 17 seconds of shaking. By the time the ground stopped moving, the city of Kobe, one of Japan's most modern, most economically vital port cities, looked like it had been disassembled from the inside. Elevated highways lay on their sides. Buildings that had been considered earthquake-resistant crumbled. The port, which had been the sixth busiest in the world the day before, was destroyed. Over 6,400 people were killed. More than 300,000 were left without homes in January, in winter. What the Kobe earthquake exposed was something architects and engineers had assumed they'd solved. Modern infrastructure, designed with seismic codes, built with precision, inspected and certified, was not enough. Not because the engineering was bad, but because the assumptions the engineering was based on were wrong. The models hadn't accounted for the precise nature of that fault, the soil liquefaction, the duration of specific frequencies. Now scale that up. Kobe was a 6.9. A full Cascadia megathrust is a 9.0 or higher. That's not a little bigger. Because of the logarithmic nature of the Richter scale, a magnitude 9.0 releases roughly 180 times more energy than a 6.9. And then, before infrastructure response teams can even assess the damage, a San Andreas rupture compounds the disaster. Kobe is not the worst-case scenario. Kobe is the preview. The west coast of the United States is not just a regional economy. It is the engine of the global one. The ports of Los Angeles and Long Beach together form the largest port complex in the Western Hemisphere. Roughly 40% of all containerized imports entering the United States flow through these two facilities. Silicon Valley, Seattle's tech corridor, the agricultural networks of the Central Valley. These are not isolated systems. They are nodes in a global supply chain that the entire world depends on. A dual fault rupture scenario would not simply damage cities. It would sever infrastructure arteries that have no short-term replacement. The port disruption alone would trigger supply chain failures that economists estimate could cost the global economy hundreds of billions of dollars within the first 90 days. Semiconductor components manufactured in Asia and routed through West Coast ports would stop moving. Agricultural exports from California, which supplies a significant portion of the world's almonds, tomatoes, and wine grapes, would be indefinitely disrupted. The technology sector, whose physical infrastructure runs on continuous power and cooling, would face outages with cascading consequences for cloud services relied upon by businesses across every continent. Insurance models built on single-event catastrophe assumptions would face losses no single event was designed to cover. And beneath all of this, a harder truth. The population of the Pacific Coast has grown enormously since the last major geological event. The infrastructure was not built for what's coming. Emergency response systems are designed for regional disasters, not simultaneous mega-events separated by minutes across a 1,500-kilometer zone. The economy would not pause, it would fracture, and fractures at this scale take not months, but decades to fully repair. Scientists are careful to say that this is not a certainty. The Mendocino Triple Junction connection is a hypothesis supported by significant evidence, but the Earth doesn't share its plans. What we know, both fault systems are overdue. The San Andreas southern segment has not had a full rupture in over 300 years. Cascadia has not fully ruptured since 1700. The stress is accumulated. The physics is real. What we don't know, the exact trigger, the exact timing. Whether a Cascadia event would push the San Andreas pass threshold immediately, or simply nudge it closer to a rupture that might happen years later. The models are improving, but the Earth operates on timescales and with complexities that humility requires us to acknowledge. What comes next? The research does not end here. New ocean floor monitoring networks are being deployed. Paleoseismology, the study of ancient earthquake records in the landscape itself, is expanding our picture of the past. Early warning systems on the West Coast, once nearly non-existent, are now partially operational, giving seconds to minutes of warning before shaking arrives. Seconds and minutes matter. They are the difference between an elevator that stops at the next floor and one that plummets. They are the window in which bridges go to their locked position. Surgeries are paused, trains break. The investment in those systems is not hypothetical safety theater. It is infrastructure for a future event that the geology has already scheduled. The Earth does not negotiate. It doesn't issue warnings in advance. It doesn't wait for the timing to be convenient. What it does do is leave records in the sediment, in the rock, in the trees that died when the coast dropped, in the stories passed down for 3 centuries by the nations who were standing on these shores when the last great rupture tore through. The records are clear. The science is pointing in one direction. Two geological giants, long studied in isolation, are now understood to be part of the same system. And that system is not quiet. It is patient. The question was never whether the West Coast would face a major seismic event. That question was settled long ago. The question now is whether we are ready for two of them arriving together. The geology says it's possible. The evidence says it's happened before, and the clock, as it always has been, is still running.